so I can set this guy up here. The volume's okay? You guys?
Yeah, volume's fine.
Okay. Hey everyone, I'm recording already just so that once class starts, but I'm fooling around with all my wires here, so you could move forward from this if you're watching it outside of class time. All right. Where is? Okay. So this little gadget that I bought to hold the iPhone, I got an email from the person who sold it to me, the maker of it. And she says her and her friend got together and they designed this thing and they really want a review from me. And I thought that was kind of cool that they made this. It's not like some company from overseas or something, you know?
Where'd
Yeah.
you get it? Just off Amazon?
Yeah, I got it off Amazon.
Huh.
Okay, I'm ready. Hey, Edgar.
Hey, Joanne, good morning.
How you doing?
Pretty good. How are you doing?
Good, good. Is Colin with us yet?
Yeah, I am. Good
Okay,
morning.
great. How are you, Colin?
Pretty stressed.
Yeah. What are you taking?
Physics 4D, Chem 12, I think, whatever OChem is.
Are you
and
are you a
psych.
chemo engineering major?
Maybe.
Maybe.
I'm still figuring it out.
Okay. Wow. Experimenting with Chem 12.
Yeah.
So you're taking Chem 12 and you're taking Physics 4D, which I understand is, I mean, it's so abstract. And then you said psychology?
Yeah.
Well, that's probably not that bad. But yeah,
No.
those other two classes, is Jason's teaching 12 or is it Zeruba?
It's Aruba.
Okay. Yeah, just go get tutoring, go to teacher's office hours, you know, everybody's here to help. But yeah, it is a lot of load. You're taking 3 demanding classes right now.
Yeah.
So if you want to come and see me during office hours, we could talk about more about your major and such, because Colin, this is the first time I have you. So most of the students in this class have already met with me and talked about which major they want to go into. And so let's have a talk.
Okay.
Okay. Any day, 1 to 2.
All right.
Hey, Jordan. Hey, Gerardo.
Hey, good
Amani,
morning.
Luis.
Morning.
Hello.
Luis, how are your kids? Hey, David. Hey, Bon. Okay, you guys, I'm going to get started. Okay, so topic for today is what?
Tension.
No.
Friction. Friction.
Yes, friction. Uh-oh, I haven't found my little list of all your names. Where the hell is it?
You just call on Amani repeatedly for the whole day. That'll
The
work.
whole time. The whole time, Amani, you're going to be on.
All right.
Just kidding. Damn it. I thought I was all prepared.
What did I miss? Oh, geez, there's a lot of chaos already.
What was that?
Class
Dave?
seems chaotic already.
Shut up.
It's November 3rd.
Okay, it wasn't supposed to be chaotic. I got all online. I'm all ready. The only thing is I can't find the list of your names. So anyway, let's get started. So today's class and Thursday's class already, you growing a mustache, Dave? Or no,
It was a
shaved?
Halloween costume. It was a Halloween
Ah,
costume,
okay.
and I honestly forgot about it until just now.
Okay.
And now it's November. It's great.
Yeah, it's supporting men's health or something, right? Is that what
Yeah,
November's
that's
about?
right.
Great.
Okay. All right. So today and Thursday are friction. So my plan is we're going to look at the 3 problems today and discuss them first, and then we're going to do them together. And then on Thursday, I'm going to give you a more complicated problem and I'm going to put you in breakout rooms. But we'll see how far we get because today is a quiz day. We may only get through solving a couple of problems. So, and then of course, at the end of class, we'll look at, the overview, how we always do, just to like summarize the process. But you know how to solve these problems already. The only thing that we now have is one extra equation. Amani, what's the extra equation now we have?
Friction.
Friction equation. What is it?
What do you mean? What is it?
What's the equation? Give me the equation for the friction.
Oh, the constant for it.
The
Forgot what it's
frictional
called.
force is equal to.
It's equal. Hold on. The friction force is. I'm not focused.
Okay, let's go to
It's not a good
Angel.
day.
Let's go to Angel.
Hello, good morning.
This is kind of a crazy day today, right? Election day.
Yeah.
Anyway,
got no
okay,
sleep.
Angel, what's the friction equation?
It is normal force times the coefficient of friction.
Right. So the frictional force is equal to, so whenever anybody's asking for an equation, you have to have an equal sign in it, right? So I want to hear the whole equation. It's the frictional force is equal to mu n. So which mu do you think we're using in the statics class, Angel?
I think it's the mu s.
Yeah. Wow. Yes, we're using the static friction, the part that just gets it to move. And the key in these problems, so key things. 1, we have another equation now. So Bond, boy, I'm doing so well with alphabetical order already. Bond, for a 2D problem, for a rigid body 2D problem, how many equations do I normally have?
Well, we would be able to solve for 3.
3, because what are the equations I have for a 2D body?
Some in the x, some in
Some of
the
the
y.
forces in the x. Give me the complete sentence.
Some of the forces
in the
around
equal 0.
x, some of the forces about y, and the sum of
Equals
the
0.
moment.
It's equation. You got to give me an equal sign. Some of the forces in the y equals 0 and
some of the moment about the z-axis equals 0.
equals 0. So a regularly 2D problem for rigid bodies, we have 3 equations. And now that we're introducing friction, we have a 4th equation. So now when we have 4 unknowns, we could solve it with 1 body. If we have 5 unknowns, we need 2 bodies. If we have 8 unknowns, we need 2 bodies. Okay, so for every 2D problem, we normally have 3 equations. But now that we're entering friction, we have 4 equations. When, I'm not going to be able to do this all in alphabetical order. So let's just go, okay, Isaac. When does a 2D body only have 2 equations? What kind of body, what kind of 2D body only has 2? What?
Concurrent forces.
Say it
Concurrent
again?
forces.
When
A
there are
particle,
concurrent
concurrent
forces and we're only analyzing a particle. So when we, in a 2D problem, when we have a particle, there are only 2 equations. Some of the forces in the x equals 0, some of the forces in the y equals 0. If it's a rigid body, we have 3 equations. Some of the forces in the x equals 0, some of the forces in the y equals 0, some of the moments in the z equals 0. When we have friction, we have 4 equations. Okay? All right. And we're just doing 2-dimensional problems in friction. So you really know how to solve these problems. We're just adding friction. The key thing, and of course, mu, we're only dealing with mu s. The key thing is you can only apply the frictional equation when it's about to move. It's about impending motion. So when we look at a friction problem, the first thing we really need to do is think about which way is this thing going to move. And once we know which way the thing is going to move, Dave, knowing the thing's going to move, what do we know then about the direction of the frictional force?
It will be opposing it. So if it's trying to move this way, the friction pushes against it.
Correct. Okay. So again, we're talking about impending motion. And typically, Colin, is mu s typically greater than mu k? Or is it usually less?
It's usually larger.
It's usually larger because you need a greater force of external force to push it from being static. And then once it starts sliding, then you could put mu k in. But because this is a statics course, we're only using mu s, and realize that has to be impending motion. If you have two blocks on top of each other and they're not going to move relative to each other, the force is not equal to mu n between them. Let me say that again. And this is so our schedule today is, of course, we have our quiz at the end. We have 3 problems we're going to look at. We're going to look at the problems first and talk about how we're going to set them up. Then we're going to set them up and solve them as much as we can today. And then on Thursday, we'll finish that up, and then I'll put you in breakout rooms and do a more complicated problem. The more complicated problem on Thursday, you have 2 blocks on top of each other. And if they are not going to move in relative to each other, the frictional force is not equal to mu n yet. The frictional force is only equal to mu n when it's about to move. Okay? All right. So let's take a look at the problems we're going to solve. And now this is what I'm going to have you guys do, because once I start sharing the screen, I'm not going to see names and I can't find my name sheet. So once you answer, then you're going to have to call on somebody else to answer next. All right. It looks like for alphabetical order, I did Colin, I did Dave, I did Isaac by accident, Bon, Amani. So we're looking at the Daniels, John, Laura, Liam. Okay, so I'm going to share my screen. Can everybody see this first problem?
Yeah, that's good.
It would be really great, again, if you guys put your faces on the screen. All right, so important thing, we got to read it. So let's take a look. There's an inclined surface. There's a block on it. The inclined surface is at a 30-degree incline. The weight of the block is 500 pounds. There's an external load P that's being applied, and it's 20 degrees from the top of the block. And mu s is 0.2. So the question says, determine P for the block to be in equilibrium. So you're basically determining what the P minimum is and P maximum. And right now, me mentioning P minimum and P maximum, you might be totally confused. But let's think about what's happening. So, Liam, if P is a very large number, what's going to happen to the block? Liam.
The block's gonna move
Which way?
up the incline.
Right. So if I apply a large P, it's going to move up the incline. Okay, Luis, if P is very small, what's going to happen to the block? Luis? Okay, Laura, if P is very small, what's going to happen to the block?
Oh, Luis answered. He said start sliding down.
Oh, thank you. Did he do it on the chat?
Yes.
Okay, thanks, Laura, for monitoring that. Sorry, Luis. Good. So if P is great, the block's going to slide up. If P is little, the block's going to slide down. So do you understand why there's a range of values for P?
Yeah.
Right? So when we use these equilibrium equations, we're looking at static equilibrium of it not moving. So Laura, what do you think we should do when we analyze this block then?
We probably need to determine the we need to for sure get a free body diagram, but C, test mu s with the minimum power, find like the minimum power required or load.
Okay, and I just used the word P, but it doesn't represent power, it represents force. So if P is large, the block goes up, and if P is small, the block goes down. So when we draw a free body diagram, what are we gonna do?
We're
Think
gonna
about
do
that.
2 different ones for each situation.
Excellent. We're gonna need to analyze it 2 different ways. We're gonna analyze it first with, well, one way with the block sliding up. And if the block is sliding up, which way is our frictional force going, Laura?
In the negative direction.
Down, right? And
Yeah,
if we analyze it with the block sliding down, which way is the frictional force going?
up the incline.
Up. Does that make sense, you guys? So when you look at friction problems, you first have to figure out which way is this thing going to move, because that tells you which way to put the frictional force, which direction. We know the frictional force is always parallel to the surface, but it needs to oppose the movement. So in this type of problem, the block can slide down or the block can go up. So we have to analyze it in 2 different ways. Okay, so we have to analyze it with one free body diagram with the block going up, and then we need to analyze it again with the block going down. Okay, so another thing that I want to ask you is looking at the way this block is oriented, and let's see who, I didn't see, Edgar, how would you arrange your axis to do the minimum amount of work?
I'll set up to where the x-axis is along the 30 degrees incline.
Great. So, and I'm guessing the reason that you're doing that you want to put the x-axis along the incline is because the frictional force is going to be in the x, the normal is going to be in the y, and that's all we have to find the components of is P and W.
Correct.
If we put the x and y axis the way we normally would, the only force that's in the x or y would be the W, and then we have to find components for 3 things. So we really want to look at this friction problem first with finding out where the hell is this thing going. And then the other is figure out how we want to orient the axis. Okay, so now we're going to go on to the second question. I'm hoping this is okay with you that we talk through the 3 problems first. Everybody, thumbs up? Okay. Okay, so let's take a look at the second problem. Oh, and by the way, whenever we deal with friction, the possible motion is sliding, sometimes it's called slipping, or tipping. The only thing that's happening with this block is it's either going to slide up or slide down. But let's just take a look at number 3 for a minute. Have you guys ever pushed a refrigerator and it tipped over? Hopefully not. But you realize that you want to push it low, right? Because the higher you push it, the more it might rotate. And in statics, we are trying to prevent motion, and we know how to do some of the forces and the sum of the forces in the x and the y equals 0 equations, which is preventing linear motion. And we know how to do some of the moments, which is preventing rotational motion. If this guy, nice guy, huh? You like the drawing? If he pushes the refrigerator too high, it's going to tip at A. Does everybody think that? But maybe if he's not pushing it too high, it'll slide. So in some friction problems, you have sliding or tipping, and you have to figure out which one would occur first.
Question.
Okay. Well, yes, Isaac.
How do you account for the fact that once it starts tipping, all of a sudden the surface area on the bottom is a lot lower, and so the friction force?
We don't worry about the surface area at all in friction problems, which is very interesting, because you think that if there's more surface area, there's more friction, and it's not true. So we're always looking at these as if they're just a plane. Well, how we do account for it is that when it starts tipping, where is the normal?
In the back.
Say that again. So this guy, actually, I didn't mean to talk. Let's talk about this guy problem later. All right. But I want you to know that in friction problems, we're also looking at tipping as well. Okay, but let's go back to this problem. So we have this cylinder. It looks like it's a cylinder on a cylinder. It's on an inclined surface again, it's 30 degrees. And they're telling you what the weight is. There's a weight that's suspended here. I'm sorry, this is kind of confusing. The cylinder, let me just read the words. The cylinder is 250 pounds. So this whole cylinder weighs 250 pounds. They tell you that the cylinder has an inner, a diameter here of 8 inches and 12 inches. Okay, so the cylinder is 250 pounds and it has an inner and an outer diameter. It's asking you to determine the weight, this W here, and the coefficient of friction between the surface and the cylinder. Okay. So who else is here? David Lopez Rodriguez.
Yeah.
So looking at this problem, what forces are present?
There's static friction.
There's
There's
friction.
force,
Okay, there's friction. What else is there in here?
the normal force,
The normal force, great.
and the weight.
The W that's given, and then the 250 pounds of the cylinder. And where should the weight of the cylinder be?
In the middle.
In the middle,
the
great.
center.
It's center, excellent. So we have a frictional force, we have a normal, we have this W, and then we have this 250 pound cylinder. So now the question is, right? One of the first things you do on a friction problem is figure out which way is this thing going to go, right? So we have to figure out which way could it possibly go, because that's going to determine which direction the frictional force is going to go. So what do you think?
I'm thinking
David?
it's gonna roll down.
It's going to slide down. And if you're not sure about it, if you're not sure if it's going to slide down or not, you could do both. You could do up or down. But you're noticing, aren't you noticing here that if it could slide down, but it might turn going up. But again, we don't know if it's a pending motion or not. Can everybody see that the only really impending motion that we see is that it might slide down? Let me stop here. Say that again.
How can you say that? You don't know what the weight is, the W.
We don't know what the W is. So if the W is huge, right? If
It
the
might
W is
roll up.
huge, it won't slide up though. What will happen?
It might roll up.
It'll probably roll up, right? So we could try both. Okay. And it may be because I've done the problem a bunch of times that I may just know, and I have this intuition that maybe is false. Okay. So the
Maybe
first
I missed something there. It says 250 pounds. Are there two weights?
Yeah. And I'm realizing the way I wrote this is confusing. I probably, there's the weight of the cylinder. So there's a weight that David said. There's a weight of the cylinder that's coming down from the center. So let's call it WC. And then I probably should have called it P and P. There's a weight suspended from here too. There's a
It's
block.
something else. Okay, it's something
Yeah.
else hanging off of
Yeah,
it.
there
Okay.
are two weights, you guys. There's the weight of the cylinder, which is applied at the center. And then it's asking you to determine this weight of this block that's hanging on the end. Okay, so we're going to have two different weights.
It's
you-
not
So-
a hollow cylinder.
Say that again, please.
It's not a hollow cylinder.
No, it's hollow.
It's hollow, but the weight would still be concentrated at the center of
Right,
mass.
even if it's hollow, the center of this cylinder is still in the center of the circle.
Mhm.
Right? Was that Angel? Angel, was that you?
Yeah, that was me.
Yeah. Does that make sense?
Yeah.
Like,
so
even though
the
it's
W-
hollow, the weight of the cylinder is still in the center of it.
So the W that's hanging tangent to the inner radius, that's a separate weight than the
Yeah, that's
cylinder
a,
weight?
that's a block that's hanging there. I probably should have drew a block.
Okay, that makes more sense.
Yeah, sorry about that. Maybe it would be a better picture if I actually drew a block and called this WB and then call this WC. When we solve the problem, we'll do that.
Okay.
Okay, so let's go up to the first one. The first one, we talked about motion and we realized that it could slide up or slide down. So we're going to analyze it both ways. Number 2, we talked about it possibly sliding down, and we can analyze it to go, if it rotates up, we could do that too. If we're not sure, we certainly could do it. But remember, the only time you could apply the friction equation is when you know there's a possibility of something sliding. Okay? And then let's look at 3. Now, in number 1, there's only one body, a block. In number 2, there's only one body, a cylinder. But in number 3, there are 2 bodies. There's the person and there's a refrigerator. So the words in the problem say the weight of the refrigerator is 180 pounds. The weight of the man is 150 pounds. The frictional coefficient between the refrigerator and the floor is 0.25. And between the man's shoes, because he's wearing rubber soles, and floor is 0.6. And you know, it's really interesting is you could look up what the coefficient of friction is between 2 different materials. In fact, I could give you some. I thought that was really interesting. If it's metal to metal, it's usually 0.5. If it's wood to metal, it's 0.5. If it's wood to wood, it's 0.4. If it's leather to wood, it's 0.4. Rubber to metal is 0.5. Rubber to wood is 0.5. Rubber to the pavement is 0.7. You don't need to know those numbers. I just think it's kind of cool to know what material and then know, right? So refrigerator, notice the coefficient of friction for the refrigerator is less than the guy because the guy has rubber shoes on. The floor is the same. But refrigerators are allowed to move somewhat, right? In case we have to push them. So the frictional force is less. Okay, so let's talk about impending motion. So I have to see who else is here. So I'm going to stop sharing for a moment. And okay, so let me go on the M's.
Joanne,
Yeah.
there is a chat that Isaac sent that has a list of the alphabetical order.
Oh,
I dug it
great.
up from Canvas from like 10 years ago.
Oh, okay, great. So now how do I get the chat and the screen and your faces?
I can email or text it to you.
It's a text it. You have my cell?
Yeah.
Oh no, I can't. Don't text it. I'm using the camera. All right. So let's do Marcin. So Marcin, we're looking at 2 bodies here. We're probably going to have to analyze 2 bodies, right? So it's asking, can the man move the refrigerator by pushing? So Marcin, you're here, right?
Yeah.
Okay. So which way would we want to draw, if we're looking at the refrigerator only, which way would we want to draw the frictional force on the refrigerator?
To the left.
Correct. Say it in a more assertive way.
To the
Because the
left.
guy is trying to push the refrigerator to the right, right? So which way is the frictional force going on the fridge?
The left.
Right. Okay. So that we know. Okay. And Marcin, let's figure out this guy. This guy is pushing the refrigerator. If you think about pushing a refrigerator or something heavy, which way will you might move?
I will be moving to the right.
Maybe I should have you go move a refrigerator. If you're on a tile floor that's slippery and you go to push the refrigerator,
Oh, if
which
I'm
way
not,
to say
if
it
we're
again?
being realistic, I won't actually get to push it. So I'll be moving left as well.
Right, you're gonna move left. So, I mean, you're trying to take steps, right, and push the refrigerator to the right. But if you're staying still with your feet on the ground and you're pushing the refrigerator, if the friction between your feet and the tile is not that great, you're going to slide backwards. You're going to go to the left. So should we think about that more? if you tried to push something, right, and if it was really heavy, you might slide backwards. So the refrigerator movement is to the right, but the person movement is to the left. Let's talk about that because I think I'm stumping you. Anybody want to talk about that?
Is that
Yeah, I
when
have
the
my doubts.
equilibrium, or
Say it again.
is that when the system is static?
Well, we're analyzing it for static equilibrium, but we have to put the frictional force in one, draw it in one direction, which means when we have to determine its direction, we have to figure out which way we're sliding, right? So even though we're doing a statics problem and nothing is moving, I have to think about how I would be moving or it would be moving because I have to draw the frictional force in the opposite direction. If you push something that's very heavy and you can't move it, you wind up sliding backwards. Your feet are going to give out from underneath you.
But once you start moving it, then you move the opposite direction.
Yes, but once you're moving it, we're not in the class anymore. We're in the dynamics class, right? But we could analyze it in both directions. In the end, you're going to find out because you're going to wind up getting a negative, right? You'll get a negative value for your frictional force. But it's good in these, because these problems are a little more complicated, it's worth it to spend the extra time thinking about the possible direction of the motion. Okay, so I'm going to go back.
I have a question.
Mackenzie, yeah.
So if the person sliding to the left, is there friction going to the right then?
Then the frictional force goes to the right, correct.
Would their frictional force and the refrigerator's frictional force cancel out if they're like meeting each other? Or
well,
would they?
That's a really good question. When I did this problem, I separated the refrigerator and the person. And in both cases, I had the frictional force going in an opposite direction. But what your question is, will the frictional forces cancel each other out? They won't cancel each other out because the frictional force is mu n, right? And mu is different between the man and the tile and the refrigerator and the floor.
Okay.
And then also n is going to be different. I think in this problem, the refrigerator weighs more than the guy.
Yeah.
Right?
Okay. That makes sense.
So that's probably a better answer for your question.
Yeah. Thank you.
Okay. Okay, great. Other questions before we start solving the problems? No? Okay. Here it is. Okay, so let me share the screen again.
I emailed the list to you.
Oh, thanks. Okay. All right, so let's start with the first problem. They get a little more complicated as we go on. Okay, so actually, before I share, to try to get through more problems, do we want to not do the complete setup, or do we want to do the complete setup? Do we want to move ahead a little straight to the free body diagrams?
I think the setup is pretty important.
Okay, so let's do it. Yep, I agree.
Can we focus especially on, because I was looking at the homework and you asked for a range of values of P. Could we go over like how to find this range of values? That seems to be the newest concept.
Yep, and that's going to be in this first problem. So let's do it. Okay. So could everybody see my paper? Yeah. Okay.
Yeah.
So I'm going to start up here. So given. So we always have the sketch info. And then we're given that mu s is 0.2. And the rest of it's in the block. And then find. They want to know. Yes, I started recording before class started because I wanted to get
that it's recording. Is it recording your your document camera.
Yes, I totally know how to do it now.
Excellent.
Okay, so we want to find P min and P max. Okay, so when we looked at this problem, we looked at the block and we were trying to figure out which way is it going to move. And we said that if P is large, it's going to go up. And if P is small, it's going to slide down. So we have to analyze it in two directions because in each way, the frictional force is going to be in a different direction. So let's look force, magnitude, direction. And what forces do we have present? We have the weight of 500 pounds. So we have that. We have a normal, but we don't know the normal, but we do know its direction. We have P, we don't know that. We have the frictional force, we don't know. Is that good? We have, am I leaving any forces out? We have the weight of 500, we have and if I were writing, if I could write on my screen, I would start writing this as scrap and just drawing it on here. I have the weight, I have the normal, I have the frictional force in P. So, and then mu is given, right? Sometimes they ask you for mu, so be careful because if mu is not given and it's in the find, that's another unknown. Did everybody hear that? Sometimes these problems ask you for mu. So make sure that you look back up at your find because there's no really way for us to put our mu s in our table. But if they're asking you for mu, that's another unknown. But in this case, we have three equations. We need three unknowns. It's a 2D body. We need one body. Okay. But in terms of the frictional force, we know the direction, but we don't know if it's down or up. So we really have to analyze it two ways. So I'm going to say slides up, slides down. So if it slides up, let's draw our free body diagram for both. And this is 30 degrees.
I have a
30
question.
degrees. Yeah.
Does anyone know how to make, like, you know how Joanne's sharing her screen? I can only see what she's writing on in a tiny little box in the corner. Does anyone know how to make that bigger?
Are you
Yeah,
on,
double tap on the.
I tried double tapping on that box and
are you on desktop or mobile?
desktop.
So on mine, it has a gallery view down the side, and you can pin Joanne's document camera, and then slide. There's a slider, and I'm not sure if everybody has the same setup. Zoom seems to only give it to half the people, but you can slide it over so that basically Joanne's document camera becomes big, and it'll shrink the other side.
I can't, for some reason, get into gallery view.
Okay.
Do you see three dots in my screen where I'm writing?
Hold on.
Joanne, you want what will solve her problem is also you can just, now that we have it all set up, you can just stop sharing your screen, and that way we can pin your.
Yeah.
Oh,
I can't.
okay.
Okay, now I can pin it.
Yeah. Okay. Great.
Thanks. Thank you guys.
Okay.
Sorry. Thanks for your patience.
No problem. Okay, so I have two free body diagrams drawn. So on the left side, I'm talking about sliding up, and on the right side, I'm doing sliding down. And so if it's sliding up, my frictional force is going this way. And if it's sliding down, my frictional force is going this way. Everybody good with that? Yeah. And then Edgar said he's going to make the X and Y axis like this, right? And, you know, since P applies, so I'm going to do components. So for P equals P times the cosine of 20 degrees I plus the sine of 20 degree, well, I should do cosine. cosine of 70 degrees J, and it's in pounds. So this comes out to be cosine equals 0.9397 I plus 0.3420 J. Actually, I'm going to put the P's in both spots. I'm going to put a P I and I'm going to put a PJ. Is it too small for you guys, or could you see what I'm doing?
It's okay.
Yeah, it's good size.
Okay, so then I'm going to do the check. 0.9397 squared plus 0.3420 squared, and 0.9397 squared plus 0.3420 squared equals 1. And then a positive negative visual, yes, because they both should be positive. So there's P. I got the components of P. And then I have to do this 500 pounds too. So 500 pounds, it's going to be 500 times. It's negative, let's see, this is 30, so this is 30. This is 30 here. So it's in the X is going to be negative sine 30 I plus cosine negative cosine 30J, and it's pounds again. And I shouldn't probably do all this number crunching. I already did it, but that's okay. So 30, I think, is 0.5. So it's going to come out to be 250 negative I minus, it's going to be 866 times 500, 433 J, and it's in pounds. And I'm just going to do the check. Squared plus 250 squared under the radical, 500, great. And going back, it should be a negative X and a negative Y, good.
Joanne, can you bring the paper up just a bit, please?
Yes.
Thank you.
So maybe I could have done this somewhere else, but it's going to apply to both of them because both P and F go in the, P and the weight go in the same direction in both. Okay, so I'm going to go through my alphabetical list now, thanks. Okay, Adam. Daniel C. Daniel. Okay, we're going to analyze sliding up first, right? It's a 2D problem. How many equations do I need?
3 equations.
3 equations. What are those equations going to be?
The equations would be some of the forces in the x direction, some of the forces in the y direction, and I'm gonna. We don't have a moment, so no.
What's the equation that comes with friction problems?
Connect.
The friction equation.
Yeah.
Okay, mu n. Just a hint, you guys, there are no dimensions in this problem. If they don't tell you the size of the block, you can't do any moment equations. If they said it was a square block, then you could do it. But Daniel, one thing you said is there are no moments. Take a look. These are not all concurrent forces, right? P is here. We don't really know if it goes through the center or not because we don't know the dimensions of the block. The friction force is not concurrent with the others. So there is a moment that could be created. All right. So we're going to do the force equation. So sum of the forces in the X equal 0.9397 P minus the friction force minus 250 equals 0. So 0.9397 P minus the friction force, and you want to just put it in right? Well, should we just put it in now? Yeah, let's just put it in. And we have what mu is, it's 0.2. So 0.2 times n equals 250. So do you guys see that this is I'm calling it equation 1, but it's really equation 1 and equation 2. Maybe I shouldn't do that. Maybe I shouldn't skip. Let's not skip. Let's just say this. Equation 2 is that the frictional force is equal to 0.2 times n. So that's equation 2. And then equation 3 is sum of the forces in the y. It's n plus 0.3420 p minus 433 equals 0. N plus 0.3420 p is equal to 433. Equation.
Could you raise up the paper?
Yes. Yes.
Thank you.
Yeah. Okay, by doing equation 1 plus 2 plus 3, we find out that P is equal to 334 pounds. Okay, Daniel H. Daniel Hall, you here? Okay, Danny.
Yes.
Okay, so remember, we are doing static analysis, which means when P is 334, there is no movement. It's static. But we were analyzing it for sliding up. So can you give me a conclusion? What would P have to be in order for it to slide up? We just analyzed it for static equilibrium. When P is 334, it is not going anywhere.
Okay.
But we analyzed it for moving up. So if P was what value, would it slide up?
It would have to be greater.
Yes. If P is greater than 334 pounds, block slides up. Got it? Everybody good? Thumbs up? Daniel, you listen to me or music?
Which Daniel?
You.
I'm listening to you.
Oh, okay.
I'm talking to myself while I'm doing this.
Okay, you look very excited. And I didn't think I could make somebody look that excited doing a static
Sorry.
problem.
I'm at home and
don't
I'm kind of weird.
apologize. That's great. It looked like you were dancing. Okay, so now, no dancing in my class. Just kidding. All right, so now let's take a look at this. The only difference here, we have these 3 equations, right? Where are we? Daniel, David, Edgar, Elizabeth. Okay, Eric.
Good morning.
Hey, Eric. Okay, Eric, from analyzing sliding up and sliding down, which equations are exactly the same?
I think they're all going to be the same except for equation 1.
Correct. So equation 2 and equation 3 are going to be the same, right? So I'm just going to write them down again. And I don't need, I don't have,
P.
What?
Do we just flip the sign on P? Do you move your paper
No,
up a little
because
bit?
P is the same. The only thing different is the friction force.
Oh, okay, yeah.
Right?
Okay.
Look at the free body diagrams. The only thing
So
that's
we flip
different
the
is the
sign of that
frictional force.
component.
Right. So the sum of the forces in the y is the same, plus 0.3421. P is equal to
Can you
433.
move your paper up?
Move it up, yes. So the only thing different is the sum of the forces in the x equation, right? Now it's going to be 9397 P plus the frictional force minus 250 equals 0. So 0.9397 P plus the frictional force is equal to 250. This is the only thing.
I still can't see where you're writing. Awesome. Thank you.
So this is equation 2 from the left. And this one is equation 1. No, equation 2 from the left. And the only thing new is equation 4. Right? Wait, let's see. Equation. This is 3.
Question?
Yeah.
So in our table, when we're putting in, force of static friction, we know which direction it's going to be. It might be positive or negative, but we can still count it as knowing which direction because we know the angle. Yes.
Yeah. And I mean, if you want to be complete, you probably would do a table setup for each analysis. Right? So we know it for when it goes up and we know it for when it goes down. Maybe that's better to do. But the point is that I wanted to know how many bodies I needed to analyze and how many equations I needed. So going down here now, I have equation 2 plus 3 plus 4 gave me P is equal to 187 pounds. Gerardo. You're here, right? Yeah. So, Gerardo, are you using the chat or verbal? Can anybody see?
I don't see anything in
He might have
chat.
Yeah, he might have stepped out. Hyoji, are you here? All right, Isaac, you already went. Jack? Jack, you here? Oh my God. All right, Jason. Oh yeah, Jack, you're here. All right, so in this case, I analyzed the block sliding down. And remember, it's in static equilibrium. I got a P of 187. So when P is 187, it's static. It's not sliding. What would P have to be for it to slide? Jack? But he was just here. All right, Jason.
For it to slide down?
Yeah, because we were analyzing it for sliding down.
Anything less than that?
Right. So if P is less than 187 pounds, block slides down.
Well, I'm pleased by this because I
Jason.
take 334 and I subtract 187 and I get a difference of something in the 100.
But we don't
or
want
so.
a difference. Think about it this way. So, and Jason, I'm going to have you do the final conclusion. I know if P is greater than 334, it slides up. If P is less than 187, the block slides down. So what is the range of values for P for this block to stay still?
I would take 334 and subtract 187.
Well, you can't just subtract the two numbers, right?
Well, I'm interested in that because, I mean, the range, sure, the range is 187 to 334. But
Right. So
I'm
wait,
interested
let
in-
me just write it. Would you agree that if P is greater than or equal to 187, or P is less than or equal to 334, it's in static equilibrium? Meaning it's not going to move. So you can't subtract it. I mean, if you want to subtract it, you would, no, because we're talking about a load being applied. It's a range. The load could be P, what I pull on it could be anywhere between 187 and 334.
Yeah, but it's just interesting. Like I could use that number to form a ratio with the other values, as in like the range in which it's, I don't know. Yeah, I'm just playing around.
Yeah. Okay. All right. Let's go to the. Anybody have questions about this? So Isaac, you had asked about how do we figure out a range? We have to analyze it from motion going in both directions. You guys are all smiling. What the hell are you talking about in the chat without me? Or is it in Discord? What the hell are you
You have
guys
access
doing?
to the chat too.
Yeah, you could definitely look at the chat. There's a button. for it.
I know, but that's why I think you guys are all in Discord or something.
No, we're just.
Between the two
No.
P or whatever. I'm probably not going to get your jokes anyway. All right, whatever. I don't get it.
We're engaged.
Okay, good. We're engaged. All right. So does everybody understand this? Okay. So what are some key things? First, we have to figure out which way this thing is possibly moving, because that controls the direction that we put the frictional force in, right? That's one. And then two, we have to analyze it for both directions if we think that's going to be the case. Now, were we, okay, I got to go back up to the chat so I get to the names of people. Jason Lee, I don't think I called on you. Jason, why was I allowed to use this friction equation of F is equal to mu n? When can I use that equation?
I think you can use it anytime you want, right? Because they are friction present in this question.
You could only use it when you're calculating impending motion. It's about to move.
Okay.
Right? So if your little sister stacked blocks on top of each other and tied a rope to the bottom block and slide it across your wood floor, and none of the blocks slid over each other, the only one that was sliding was the bottom block on the floor, you could only put the friction equation on the bottom block with the floor. If the other blocks were staying still on top of the other blocks, the frictional equation does not work. It only works when there's impending motion. Okay? And then the kinetic friction equation only works when there's continuous motion. Jason, question?
No question.
Okay. All right. So let's look at the second problem.
Can I see your table for that last one more time?
Yeah.
Cool. All set. Thanks.
Okay. Okay, so let's look at the second problem, and I'm going to pull it up again, share the screen. And then we'll down. So there are, and maybe I should redraw it. Let me just redraw it. Let me draw it first.
What time are we starting at? 10:30?
Yeah, what time are we looking at? Oh, man. All right, give me a little time. Okay, I'm going to stop sharing. Okay, so the problem, it says the weight of the cylinder is 250. So we know the weight of the cylinder is in the center. So let's just call it WC is 250 pounds. Hopefully this is clearer now. The weight of the cylinder is 250. There's a block here that has a weight, and let's call it weight of the block. And that's an unknown. So given is the weight of the cylinder is 250 pounds. And the find is they want to know what mu s is, and they want to know what WB is. And it said, determine the weight W, we're going to call WB, and the coefficient of friction between the surface and the cylinder. Between surface and cylinder. Okay, so
I think the weight,
Jordan,
I think the block weight is hanging from the inner radius. Is that right?
yeah, you're right. Thank you.
Yeah.
Thank you. Okay, Jordan, and notice that there was a surface here too, right? So Jordan, what other forces are in here besides these two weights?
With the surface, there would have to be a normal force and a frictional force.
Great. So we got to put a normal. And it's 30 degrees, so it's 30 degrees from the vertical. And a friction force. So now we have to decide, right? Looking at this problem, there's a weight that's pulling it this way, but there's this inclined surface. So which way?
The frictional force would be going kind of up, like to
Yes, because it's probably going to go down, slide down. So we have the frictional force going up. Okay. So we could write down assumption.
Rolls or slides?
We're doing sliding right now,
Okay.
but we could look at it both ways. Okay, we'll just try them out. It'll be, so my assumption is that it's going to slide down, which means my frictional force is going up to the right. So we do my table, force, magnitude, direction. And we have the norm.
3 things now.
Say that again?
There are 3 possibilities.
Could be. Let's see how it goes. So we have a normal, we have the WB, we have the WC, and we have the frictional force. So the normal we don't know. The WB is not given, we don't know. The WC, we know, it's 250 pounds. And the frictional force, we don't know. But remember what I said, you know, we're talking about a table that has forces and moments in it. Always take a quick look up at the find, because you also need to find the frictional force is unknown. Right? So, Luis, are you back? No. Okay, Maria. No, Mackenzie went. Marcine. Maria. So how many unknowns do I have?
4.
1, 2, 3, 4 unknowns. How many equations do I need?
4.
Right? 2D body. How many bodies?
1, because we can use the friction equation.
Yep.
And
I actually have the free body diagram drawn already, right? I kind of drew it already. So Maria, how would you like to orient the axes?
I would orient it, I guess up the, I don't know, there's 2 forces going down. And then there's the normal force and the friction force. So kind of either way would work, I guess.
Right, because we would have to break these 2 into components, or we have to break these 2 components. So you know what usually I decide it for me is what this is a known thing. And it's kind of nicer working with known components. So I'm going to do it this way.
Okay.
So if we do components for WB, where am I? Can you see everything? Yeah. So WB times negative sine of 30 minus cosine of 30 pounds. So that's negative 0.5 WBI minus, is that right? 30 sine is a half, yeah. and then 0.866 times WB pounds. 0.5 squared plus 0.5 squared plus 0.866 squared equals 1, and that's correct. Positive, negative, visual. They're going in the negative X and negative Y, yeah, okay. And then the other one is the WC, which is 250.
Couldn't you say like, because it's 30 degrees, so wouldn't it be like cosine of 120?
Yeah, I could have used that. Remember when we, at some point in the semester, we said, oh, okay, well, we could actually, this is not theta X or theta Y. You're correct, Maria. You'd have to use 120, but then you would have a positive here.
Okay.
Right. This is the same thing, isn't it? They're both 30 degrees. Yeah. Negative sine 30I minus cosine 30J. Negative 125I minus 216.5J pounds, 125 squared plus 216.5 squared. Yep, 250. Plus or minus visual. Yep, it's negative. Okay, so Maria, Matthew. Okay, is there an equation that we could use that's the most efficient that only has one unknown in it? Let's see. No.
Would it be some of the no, I was thinking some forces in the Y, but we have an unknown weight going down.
Yeah, so some of the forces in the Y would have two unknowns. Some of the forces in the X would be two unknowns. How
Yeah,
about a
because
sum
we
of
have
a
an
moment?
unknown weight.
Yeah, how about a sum of a moment?
Yes,
Yeah.
but we'd have to put it on the edge of the circle.
Yeah, let's see.
That
If we
be
put it,
because we'd have to try to cancel an unknown.
yeah, we have all the, this one, no, we don't. Yeah, if we put it on the edge of the big circle, this doesn't necessarily, we don't have that dimension. The only for sure distances are from the center. We'd have to break this into other components. So yeah, we have three equations and they all have four equations. They all have two unknowns in it. So let's just crank them out. So sum of the forces in the X equal F of F minus 0.5 WB minus 125. So I have the friction force. I have the X component of WB and WC. And it turns out to be FF minus 0.5 WB equals 125. So that's equation 1. Can everybody see my page? Okay, sum of the forces in the Y equal N minus 0.866 WB minus 216.5 equals 0. The normal minus 0.866 WB equals 216.5. That's equation 2. What did you say the third equation should be, Matthew? We have the sum of the forces in the X, the sum of the forces in the Y.
We are looking at moments.
Right.
But we also have the friction equation.
And we have the friction equation. So let's do moments about the center because then we know what the distances are from the center. So what forces, if I did some of the moments about the center, Matthew, what would it be?
Some of the moments around the center would be WB and F.
Right. So it would be The frictional force times 12, right?
Yeah. with the
Positive or
distances.
negative?
That would be positive.
Positive. And then WB times
That would be
8.
times 8 inches.
Negative or positive?
That would be negative.
Negative equals 0. So then we have 12 frictional force minus 8 WB equals 0. That's equation 3. And then equation 4, you said is a frictional force. So it's the frictional force times mu, which is unknown, times the normal. So here's my equation 4. And again, we've seen a problem like this before where a coefficient of an unknown variable is also unknown. And you really can't do matrices. You're going to have to do algebra. And when you plug it all in, you wind up getting P is equal to 1. Wait, no. Looking at the wrong problem. There's no P.
Joanne,
What am I solving for? WB. I get WB turns out to be 750 pounds. And mu S turns out to be 0.577 or just 0.58. Can you all see what I have written down? So hang on a second. W turns out to be 750 and okay, I think we should stop here and then let's just so that you you now have seen a first problem where you're analyzing up and analyzing down. And now you're looking at another problem where we are throwing in the moment equations and we have a value, but we still have the question of, well, can this roll up or not? So let's talk about that on Thursday. And then we could do the last 2 problems, okay? Or should we talk about it now and put off the quiz a little?
If you put off the quiz, you'll have to put it off for quite a while because most of us have, or a lot of us have physics
Okay.
right after this.
Okay, so let's not put it off, okay? All right, so I'm gonna go to the quiz now. So let me share the screen. Okay, so here's the friction module and here's the overview that we'll go over on Thursday. Here are the problems we're doing in class. I'll post the things. Here's the homework and here's the quiz. So let me open up the quiz. Hang on a second, I gotta move all this stuff. I have to stop sharing and get it because it's a PDF. Okay, so let's take a look at this. Frame quiz. Sorry, it's a little sloppy. Number 1, draw all forces and reactions at supports on the 5 free body diagram below. So you're given the first frame, and then what I want you to do is draw all the forces, all the reactions at the supports on all these 5 free body diagrams. Okay, so basically I took it away from its main A and F supports, and then I separated all the members, including the pulley. That's number 1. Number 2, determine the reaction at point C only. That's all I want you to do is find C with the least amount of equations. All right. And don't worry so much about how many equations, but try to do it with the least amount of equations. And you have to tell me where the equations are coming from. So you're solving for the reactions at C. you have all the free body diagrams drawn. So call them like free body diagram 1, free body diagram 2. When you write out the equations, make sure it's clear that I know which free body diagram each equation is from. Did everybody hear me? You have to specify which free body diagram the equations came from. Okay. Should I keep this up here? You might have to print it out. You know, you might want to print it out so you don't have to draw it.